So now we're going to start the section on integration. Now we're going to look at a problem here, and the problem is that if we have this function, so this is the function in blue, this is actually y equals x squared, but we've only shown it from the positive half of the x-axis. Now we want to find the area under this curve from some point A to some point B. So let's say for example A at the moment, to make it simple, is 0 and B is a value of 3. Now we can approximate that area by drawing little rectangles underneath the curve. So I'll zoom in here so you can see. So all we've done is we've split the area there into little segments. They're called partitions. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 10 partitions here at the moment. So each of them are equally spaced for the moment, and we're going to work out the area by finding the area of this little section, add this one and this one. So you can see from doing this we're going to have an error because we're going to be less than the actual required area, because we're going to be missing out, say, this little section here and this little section and this one. Now if we want, we can make the accuracy a little bit better by making the distance here a little bit smaller. So in effect we make the partition a little bit smaller, or we take more and more rectangles. So let's go ahead and we'll do that. So you can see here that we'll get a greater number of rectangles. So it means that the area here, which is an error, is smaller. And if we get even more, you can see intuitively it's quite obvious that you're going to get a better approximation to the area the more and more rectangles that we take. So let's have a little look and we'll see what the actual values. Now I know that the area of this shape here between 0 and 3 is going to be a value of 9. So if we come up here and we'll see at the top here, I've noted here the area from below. Okay, so this area here is what we have in front of us. So you can see here it starts off at 7.695 and it's 7.9, 8.12, 8.33, 8.55 and 8.77, so it's tending towards a value of 9. Now I've noted that as the area from below. I've called it from below because we've taken the approximation actually from below the curve. So we've multiplied this distance with this, and we've multiplied that height there with this distance, so we're always below the curve. So we could say that we're taking an approximation of the area from below. Now we can also take an approximation to the area from above. So you can see if we zoom in here that we've drawn out the rectangles again, but this time we're actually above the line. So it means that we're going to be working out an area that's going to be greater than 9. So this error, we'll have an error due to this point here, and an error due to this little area and this one, and so on and so forth. But again, if we allow this partition or this distance, if we call it say delta x for the moment, if we allow that to get smaller and smaller, then we'll add in more and more rectangles and we'll get a better approximation. So that is that the actual area will tend towards a value of 9. So you can see when I change this, you can see the number of rectangles increasing, and we'll get a better approximation to the overall area. So let's have a look at the actual figures here. So you can see here I've got the area from above, and we start off at 10.395 and then 10.1, 9.92, 9.68, 9.45 and 9.22. So it tends to the actual area of 9 from above. Now we could choose another point. Say for example we could choose the central point here, so say a point here, and we could work out some of the area above and some below, or we could choose any point along this partition, and it wouldn't matter which point we chose. Whenever we allow the number of area elements to head towards infinity, we're always going to tend towards the actual area underneath the curve. So let's go and we'll write down what we've learned here mathematically. So I've taken a couple of snapshots from the graphical calculator. So this one shows the approximation from above, and this one shows the approximation from below, and you can see the one from above, we've got this extra area here, so it means that we're going to have a guess at the area which is going to be too big. And we can see this one from below, we can see that we haven't included this area in here, or this one, so it means that we're going to be too low when it comes to working out the area. Now if we were to take this distance here and we'll call it delta xi, then it means the height here is going to be f of delta xi, so that whole area there is going to be the delta xi times f of delta xi. Now the overall area is going to be the sum of all of those little blocks, so I've got that written in the next page here, so I'll just head down so you can have a look at it. So we've got our f of xi times delta xi, and then we're summing up all of our little partitions, so we're summing from I equals 1 to n. So the I equals 1 to n is just this one plus that one plus this one plus that one, and so on and so forth. But notice that what we wanted to do was we wanted to make this delta xi tend towards 0. So if this tends towards 0, it means that we're going to get more and more little rectangles, and the width of the rectangle is going to decrease. And whenever that happens, we'll find that the area that we're generating, it will approximate to the actual area under the curve. So finally we can write down here that the limit as our delta x tends to 0 of the sum from I equals 1 to n over f of xi times delta x. This thing here is described or defined as the integral of the function. So we write it down with this large sum sign here, so this is the actual integral sign. So this sign here is really a counterpart to this, or a continuous form of this. So we can integrate from the lower limits a to higher limits b of f of x by dx. So let's go ahead and we'll do one as an example. If we wanted to find out the area under our curve, so our curve is x squared, then we would integrate from 0 to 3 over function x squared by dx. Now there's a rule for integrating this, and of course I haven't gone over that rule yet, so I'll just state the rule just now and then we can get our answer. So in order to integrate this, what we do is we add 1 onto the exponent and divide by that value, so that becomes x to the power 3 divided by 3, and we're going to integrate that from 3 to 0. So it's going to be 3 cubed is 27 divided by 3, which is a value of 9. So that is the area under that curve. So we'll go on to another video and we'll explain how we were able to integrate this. So that really covers the intuitive introduction to integration. I would suggest that you open up the file and have a little play with it, and you can also change the functions and put different functions in. So thank you for listening. I'll get you in the next video. Goodbye.